Good morning. Can everybody hear me? Could you guys all hear me when I was moving around too? Because I thought I was muted, but when I went to unmute it, said I wasn't muted. Did I say anything bad? No swearing? Okay, good.
I just joined anyway, so don't worry. Professor. Oh, crap.
Go ahead.
Hold on just a second. Let me just make sure. Okay. I don't know if this was a mistake or not. Have you attempted to? I already found the YouTube video, but have you attempted to take the recording of last Thursday's lecture and put it on Canvas, because it's still not up?
Yeah, there was a few people that asked about that, and I thought that well, one thing is I'm kind of regretting having the quizzes due on Sunday night. And the reason for that is I'm not going to be monitoring my email or the discussion forum all weekend long. So, Friday evening, I was pretty sure I had caught up on all the questions people had asked. But then there were a lot of questions that came out on Saturday and Sunday, some of them late on Sunday. And that,
Tried to ask mine early in the weekend.
I feel like that's a disservice to the students, right? Because if I have it to be due on Sunday night, the reason for that is so that they can put it off until the weekend. But I'm not intending to be available 24 hours a day on the weekend, especially not the last 6 hours leading up to the due time at midnight. So I'm thinking that for the rest of the term, I'm going to shift that due date to the Monday following the Sunday, so that if there are still questions on Monday, I can clear them up. So we don't have to have that problem. As to the video from last Thursday, I didn't post the link to it. That was an oversight. I had intended to post the link to it, but if you go to any of the other video links, and so I'm sharing the screen now, right?
Yeah.
So if you go to the video from the day before, let's say, it goes to the YouTube channel where all of the videos are posted. And then you could go find the most recent one, which was the one from right now that's live. But so that would be the way to find that video. The other way to do it would be to just, and I will put the link up to it. I just wanted to make sure that in case I screw something like that up again, you could also just Google ME1800 videos. Now this will give you a bigger assortment. It won't just be the ones from this week. But from this, they all go to the same YouTube channel, and so you should be able to find the one you're looking for from there. I try to name the videos with the name of the topic we're talking about, and then the term that the video is from. And so every lecture I've given for the past, I don't know, 7 years now has been on video. Most of those videos are on YouTube. So you can go find my good ones and my bad ones if you really care. So I think you do. And somebody was asking if they could retake the quiz. And the quiz, so when it was first posted, it only allowed one attempt, but we fixed that on Thursday or Friday. So as soon as somebody tried to retake it and they realized that I had made a mistake, so that was fixed. So that quiz allows unlimited attempts. If you remember from when I was talking about it on Thursday, I intended for you to do it more than once, especially if you got an answer incorrect, which is why I had it telling you the correct answer when you got one incorrect so that you could use that to troubleshoot building your Excel spreadsheet model. And I think there was a few people that still had questions about what I wanted you to do in Excel. So let me just do an example. So let's see if I go Windows key R and type Excel, E-X-C-E-L, that opens it, usually. Hey, that's working. All right, well, that is opening. Blank workbook, please. All right, so I've got my Excel workbook thing here. Let me go get a quiz question. Assignments. Quiz 3 Sunday. Preview. Come on, preview. There it goes. All right, so let's pick this one. Question 2. Now, what I like to do, just so I don't forget what I'm doing, is Windows key run snip. Oh, come on. Windows key run snipping. Nope. Maybe it's not installed on these computers. Snip. Snip and Sketch. They changed the name of it. That's why.
You can also hold Shift Windows S.
Yeah, I just want part of the screen though. Does that just open this app up? And I'm going to copy that to the clipboard, go back to Excel, and paste it in the clipboard. Now it's harder for me to forget what it was I was working on if I paste the question in there. And so it's a milling operation, a spindle speed, 6,000 RPM. So we know the speed is 6,000 RPM. We know the feed is something. We know axial depth. We know radial depth. All right, so speed, this was in RPM. Feed was in inches per minute. This is inches. I always want to make sure I keep track of the units because I want to make sure that I'm making sure the units cancel, right? So, all right, and so I'll just put in the numbers that came with this problem. So 6,000, 54.5, and 0.25. What's the question now? What's the material removal rate? And that's going to be in inches cubed per minute, right? Now, how could we possibly find out inches cubed per minute from the information we have?
There are 3 things that are inches per minute.
Oh, these are supposed to just be inches. That's Excel automatically thinking it knows what I mean.
I love that.
I wasn't looking when I was typing. I was saying inches and it did it again.
Oh, beautiful.
There. Now it makes more sense. So if we know the feed in inches per minute, we know the depth in inches, and we know the width in inches. Axial and radial depth, one of them is the depth down, the other one is the width of cut. I never remember which one is which, but I do remember that if I go to my ME1800 equations spreadsheet, ooh, it's labeled. Radial depth is the width of cut. Axial depth is the depth of cut. Okay, so now I remember that. And if I want to make sure that I don't forget that with my problem here, I can again snip that, copy it, and go back to Excel. I could paste that so that I don't forget that. But so if I take axial depth, radial depth, and multiply by each other, now I have an area, right? And if I multiply that by the distance per minute that area goes through, so this equals this one.
Excuse me, I'm so sorry.
Times this one, times this one. And the RPM was information you didn't need. If this unit changed to inches per flute, though,
You need to change it to.
then you would need to know the number of flutes and the RPM to convert it to inches per minute. And that's probably what I meant to have you do, but the problem says inches per minute, so it's simply multiply the feed rate by the axial depth and the radial depth, you get inches cubed per minute. And so that's what I mean for you to do. And then you could say, what is this? Material removal rate, and you could name the little sheet there so that next time you want to do a problem like that, you can come back to that sheet. So that's the intent. And we won't be collecting the Excel spreadsheet again unless you make some changes to it and you want me to look at it, and then we can just do that. But the idea is that you build a set of mathematical models that you can use in answering further questions, whether they're part of this class or for something else, and to learn the skill of doing that. Okay. And I owe you guys some grades back. Don't save. So I will commit to you that if you don't have all your grades back by the time we start lecture on Thursday, there won't be a quiz this week. But you'll still get credit for it because it's still in my calculation of the grades. So if I don't get all your stuff back to you by Thursday this week, we won't do a quiz this weekend. Is that a deal? And from now on, I'm going to have the quiz due at midnight on Monday instead of midnight on Sunday, so that if there are questions that come up over the weekend, I have a chance to answer them without having to be sitting by my computer all weekend. And if you choose to be sitting by your computer all weekend, that's on you. All right. What else are we doing today? That's not what we were doing today. And I'll go back and paste that, post that link. Let's see. I mean, it's part of what we were doing today, I suppose. All right, back here. Week 4, GD&T. Does anybody know what GD&T stands for before we move to the next thing? Anybody? Jump in, type it in the chat. If you had to guess what, all right, now you have to guess what GD&T stands for, because I want you guys to exercise your fingers and wake up. Type in the chat what you think GD&T means. Type quicker. Gap dimensioning and tolerancing. Not quite.
For a second, I thought you were telling us the correct answer, and I was like, dude, you
Keep
want
going,
us to
keep
type,
going.
but you're just giving it? No.
Keep going. Keep typing. What do you think it is? Good day for tacos. 3 little cat ears. I'm not sure.
Every day is a good day for tacos. It's Taco Tuesday.
I'm pretty sure it's turning Tuesday. No. All right. If you
Tacos and
not
turning.
enough of you have typed, it's geometric dimensioning and tolerancing. Abby, you said geometric dimensioning and tolerancing. How did you know that?
From a CAD class.
Yeah. So then when I asked, does anybody know what it means? How come you didn't speak up?
I don't know.
You don't know.
I typed it.
You did type it. Yeah. Man, this term is tough. I'd like to see the people because then in the classroom, when you're sitting out there, I can say, you in the red shirt, what does it mean? And I can put you on the spot. Are you wearing a red shirt? I don't know. Can't see.
See?
You don't have your. Oh yeah, look, Brian's wearing a red shirt. I can put you on the spot.
I wouldn't even have a good. I wouldn't even be have a good guess like good day for tacos.
So, all right. So geometric. I could stop complaining about how much I don't like this term because I'm guessing you guys don't like the term that much either. Geometric dimensioning and tolerancing.
I like it.
What the heck does geometric dimensioning and tolerancing mean? Did I tell you how my daughter's 4th grade class is being conducted this year?
Oh boy.
At 8:30 in the morning, she logs onto a Zoom call. And at 2:30 in the afternoon, the Zoom call is over. And they sit in the chair all day long. She gets 15 minutes recess in the morning, a half hour for lunch, and 15 minutes in the afternoon. I can't believe that it works, but she sits there all day long doing her schoolwork. It's amazing. Any of you guys sit in your chair for 6 hours every day just doing Zooms and schoolwork?
That
Click yes in the participant. If you spend 6 hours a day sitting in your chair. 6 hours a week, David says. This class should take more than 6 hours a week.
No, he's saying 6 hours is a week. Rookie numbers.
Oh, is week. Oh, got it. Yeah, I guess, I don't spell well, but he did spell week the other way. Depends if I have lab or not. Okay. All right. What does geometric dimensioning and tolerancing mean? More people talk. You don't have to be on camera to talk. Just talk. What does it mean? You can type it.
I'm wondering if it's something similar to. Oh, did you want me to type it instead of saying?
No, you can talk.
If I had to throw a guess, it sounds almost self-explanatory. It's like trying to in something in say SolidWorks add dimensions and tolerance.
Right. So geometric, we understand, right? It's the geometry of the thing. So you guys all have one of these, right? A Y block. So there's geometry of this. So dimensioning. What's a dimension?
Nominal distance.
So dimension is a distance. Does it have to be a distance? In this case, we're talking about distances anyway. It's always a length.
Well, it could be like angle.
Geometric dimensioning. So it's a length on the part, right? If it's a length, so geometric dimensions, that we understand. It's how wide is the Y block? How far apart are the holes? How big is the chamfer on the edge of the Y block? Those are all dimensions that we can wrap our head around. We can understand them. They're Euclidean dimensions, right? Or, yeah. So if those are dimensions, what's a tolerance?
How wrong those dimensions can be without major problems.
Yeah, so the tolerance is simply how much So the tolerance is how much is the designer willing to let us screw up as we're the manufacturer? We're the manufacturer. How much is the designer willing to let us screw up and still accept the part? So now, why does the designer want to let us screw up?
For the job application, it might not matter.
Okay, so the designer's willing to let us screw up on some of the dimensions because they might not be critical to the function of the part. That's fair. Why else might the designer want to let us screw up?
It's cheaper because you don't have to throw away parts.
It's cheaper to make the part if you're allowed to screw up in a bigger way, because then more parts are good parts. Why else? Why is it required for the designer to allow us to screw up? So they might want to let us screw up because it makes the whole process cheaper. But why do they have to let us screw up?
Because it's really hard to have
We suck.
all the parts. It's really hard to manufacture all the parts with the same size. So to make doable the process, you need to have a margin of error.
So it's harder for us to make all the parts if the tolerances are tight. If the designer says, but if so the less screw up that the designer is willing to accept from us, the smaller that's going to be, the harder it is for us to do it. And that means it's more expensive for us to do it. But Matthew's got it right. Nothing is going to be absolutely perfect. And even if it was absolutely perfect, there's another reason. So besides the fact that we probably can't make it perfect, because there's no process that doesn't have some inconsistency in it, there's another reason that we have to be able to screw up. It's impossible to measure with 100% accuracy. So when we look at tolerances, the ability to make the part is important, but also the ability to measure what you think you made is important. So I could very easily make the part exactly the right length, but I will never know that I did because I don't have a measurement tool that can measure it exactly the right length. Even when I get a calibrated standard from the National Institute of Standards, it has an uncertainty that comes with it. Remember, we talked about measurement and quality. We talked about the fact that all measurements have some uncertainty. So if we always have some uncertainty, we never know that we got the part correct. Now, GD&T and GPS mean the same thing, sort of. What's GPS mean?
Global positioning system.
You might think so. What else does GPS mean? Geometrical product specifications. And I know this because the International Standards Organization defined it to mean that in ISO 213. And if you are in Germany and you made my parts and you shipped them to me, then the parts you made have to conform to ISO 213, the dimensional and geometric product specification, or the GPS specification. And if I say your parts are the wrong size and you say they're the right size and we go to court over it, it's going to matter whether or not they're the right size according to this ISO definition. What is ISO? Have we talked about this before? We've mentioned it in lecture, but I don't think we've really talked about it. What is the ISO?
You mentioned it. The International Standards of Operation.
So it's the International Standards Organization, but what the heck does that mean? What's a standard in this case?
Expectations, legal limits.
like a certain level of tolerance and precision.
So levels of tolerance, position. So Matthew says in the chat that it's defining what's right or not. It's not quite that. What? So you can type it in the chat. That's fine. I can read. I get the chat window just over the right shoulder of the camera here. So if I'm looking above you and to your, I guess that's your left shoulder. If I'm looking above you and to the left, that means I'm looking at the chat window, and only Matthew's going to type. There we go. Defining specific lengths. And so standards can do that, but that's not the kind of standard I'm talking about. That would be like a physical standard, and that would be like a thing like in Paris in a museum, they have the meter. It's a piece of gold with two lines scratched on it that are a meter apart from each other. We don't use the meter anymore. Now we use the speed of light, the distance light travels over a certain time to measure length. But make sure things are what it says it is. That's close, Isabella. So the standard is a document. It's a book. The standards organization is a publishing company. They publish the books. And what it does is it's a set of rules that a committee of people have gotten together and agreed that this will be the set of rules that we use when we talk about this thing. And so there's standards for how you put markings on drawings for when you go to the for when you make your drawings. So some of you have had ES 1310, the CAD class, right? And you pick an ISO layout or an ASTM layout, probably, right? Or ANSI layout. So it's either an ANSI drawing or an ISO drawing. So you pick that, and then the box looks a little bit different depending on which one you have. And then the way you annotate the drawing, so the way you say, this is the length, or the way you write down your tolerances, those are defined by that standard. So that if you send me a drawing, one, if there's markings on the drawing that I don't understand, that I've never seen before, I can look them up in the standard to know exactly what you meant, because we've agreed in advance that that's the document we're going to use to control how we write stuff down. So GD&T is controlled by standards. Okay, so that's cool. That controls how we mark it down on the drawing. Did you guys learn about this in CAD class? Somebody that took ES 1310, tell me, did you learn about this?
All.
A little bit, yeah.
A little bit.
Yeah.
You guys talked about it. In ES 1310, you talked about how to correctly put the symbols on the paper. Now, I actually took ES 1310 here. I took ES 1310 here in probably B term or C term. So it was either 1989 or 1990. If it was B term, it was 89. And if it was C term, it was 1990. One of the first things they taught us when I took ES 1310 was how to roll the pencil as you pulled it across the paper so that the line thickness would stay the same all the way on your line. So it wouldn't change line thickness through drawing on the paper. Now, they had invented computers by 1989, and we did about half the work with paper and pencil and about half the work on the computer. And I do remember working on my final project for the class, sitting in this big, I think it was HL230. I think it was the same space where HL230 is now. It was configured differently then. Sitting in that room, and the lights flickered, and all the computers on the other half of the room turned off. I hit Control S, Control S, Control S, Control S, and then all the computers on my side of the room turned off. But all the people sitting on the other side of the room lost their project, and I got to save mine. So that was kind of cool. So save early and often.
Click save, damn it.
Exactly. That's why that slide is in the instructions. So, all right. So standards tell us how to write the stuff down. And you've seen drawings like this one where this is our Y block, right? There are some critical dimensions on this Y block, and there are some very much not critical dimensions on this Y block. Would you agree? Having seen it, having seen how it goes together, what dimensions are important to me, the designer here? Or based on the drawing, what dimensions are important?
The distance between the two tapped or threaded holes.
So I care about the distance between those two threaded holes, because if they're too far apart, I can't put the clamp on it and put the fasteners through it, right? And if they're too close together, I can't put the clamp on it and put the fasteners through it. So if I had to find out, and so what is my tolerance for those? Can we see on this thing? It's kind of hard. It says 3 decimal places. I'm willing to accept plus or minus 0.005 inches on that location. Now, how did I decide that? So in ES 1310, they talk to you about how to write it on the drawing. How do you decide what number to put there?
I would assume it's like partly based on like the standard itself, and then also how much you tolerate as the designer.
Yeah, so the standard itself does not tell you how to pick what the dimensions or what the tolerances should be. It simply tells you how to represent them once you, the designer, have decided. It is the designer's responsibility to decide. So how do you decide? Who in the class say yes in the participation thing if you've ever created a drawing or a sketch, and no if you never have? This means everybody should answer either yes or no, right? This tells me who's sleeping or making breakfast or doing CrossFit
or running.
Somebody clicked on go faster instead. Yeah, me too.
Some people are also responding in the chat.
Oh, okay. Yes. That's
A
fine.
lot of people.
All right, perfect. All right, so we have some experience making a sketch. Most of us do. Those of us that said no, I'm sure you could imagine doing it, right? So if you were making the sketch, so you already knew what you wanted your Y block to look like, and you're making the sketch so that you could tell me what you wanted your Y block to look like, how would you decide what tolerance to use? You guys are engineers. How would you decide? So
I mean, for the bottom of the Y block, if you wanted like a tight fit or a loose fit,
right?
Tolerance,
So where the bottom goes into the base, right? Because that sits down in a pocket recessed into the base. If it's bigger than the pocket, it won't fit in unless you have a really big hammer. And if it's too much smaller than the pocket, it'll wobble around when it fits in. So that's that. But let's just think about the distance between the two holes. How do you decide what the right dimension is? I will tell you what I did. I just made it up. I guess. I knew plus or minus 0.05 wasn't hard for us to hit. So I just said that would be the dimension. And then when I made them, I put some together and they worked, so I declared victory. That's what I did. Is that the best method?
No, not.
It works in this case because that the little clampy thing that we use on the top, it's got a bunch of compliance in it. Sometimes we get the holes too close together because we bought different clamps, or sometimes we get the holes too far apart because we bought different clamps. But you can usually get the fasteners in. So on this, it wasn't really an important dimension, but let's think about where, I don't know, where might it be an important dimension?
With the piston head.
Oh, the axle on your car. If the two wheels don't, if the two front wheels or the two back wheels don't point in the same direction, is that bad?
Probably.
So getting that right might be important. Let's think of an aircraft carrier with a nuclear reactor to supply the energy to turn the electric motors that turn the shaft that go out to the propellers that push the thing that's a mile long. I don't know how long they are. They're huge. That push the aircraft carrier through the water at 30 miles an hour. Could you imagine misaligning the motor and the shaft? Would be bad. What it would cause? It would cause a lot of vibration, and it would cause the whole thing to fly apart. Anybody ever seen a big wind turbine? Yeah, most of us have at least seen pictures of them. Anybody ever seen one on fire? Yeah. So I've seen, and that happens when things get misaligned. So they're out of tolerance. They get misaligned, friction builds up. And I've seen one, it was a picture, I didn't actually see it, but it's a picture of one in the North Sea, offshore, off the coast of Norway. And they get the little like housing on top. So the one I was looking at that was on fire, that housing is the size of a freight train car. So those aren't small. Anyway, all right, so screwing up the tolerances is bad. Who's ever put something together? Who's ever assembled something? Put two things together, put a screw through the things to hold the two things together, maybe? So you guys have done that? Okay, here's my tolerate slide. Here's the definition of tolerance from the standard. The allowable deviation of a standard, especially the rate of variation. You can read that. All right. So let's look at this sketch here. So disregard whether or not it's dimensioned correctly, because I know that this leader here shouldn't cross the dimension lines and stuff like that. So we violated some rules, and we've dimensioned it on the, I guess this is an isometric projection. Disregard that stuff. Let's just think about the tolerance numbers. So if I was going to, through one of those holes, and what's the diameter of the holes? Those holes are 1 inch in diameter, right? Nominally. So the holes that go through the part, there's 4 of them. What's the biggest that one of them is allowed to be?
1.01 inches.
1.01 inches, right? And so how big is that in our machinist technobabble? It's 10,000. So 1.01, but it's an inch plus 10,000, right? So the 0.01 is 10 thousandths. And how small could it be?
1 inch.
It could be 1 inch. Okay, so if I had a shaft that measured 1 inch, would it always fit in the hole?
Not if that shaft also has tolerances.
All right, so the shaft also has tolerances. So let's say we're going to manufacture shafts, a shaft or multiple, that are 1 inch plus 0.01 minus 0. Would it always fit in the hole?
No.
No, sometimes it would fit in the hole. Sometimes it wouldn't fit in the hole, right? Because it depends on how big the shaft is and how big the hole is, because they both have the exact same tolerance. Now, what if I had a shaft that was 1 inch minus 0.01 inches plus 0? Then would it always fit in the hole?
Yeah.
Okay. All right. So I'm going to switch over to stop the screen share for a second. So if I have my plate, it's got one hole in it, and we said that that hole was 1.005 plus minus 0.0005. Sorry, 005, right? And so this means it goes from 1.010 to 1.000. So that's the range that the hole can be. And if I've got a shaft, and it is 1.000 minus 0.001, sorry, 01 plus 0. All right, so that shaft always fits in the hole. And if we had 2 of these plates and we stacked them on top of each other, we could always put the shaft through and it could locate the 2 plates relative to each other, right? Except they'd be able to spin relative to each other because it wouldn't orient them, but it would at least put them together. Now, what if the shaft was bigger than the hole? Could I still assemble it? Could I still assemble it if the shaft was bigger than the hole?
Maybe, but you probably shouldn't.
I don't know. It depends on your intent. I could press harder in the shaft would go in the hole, right? And we sometimes do that. We call that an interference fit, where we know that the shaft is bigger than the hole and we want to push it in because we don't want it to come back out again on its own. We want it to stay there. So in this case, we want it to be a slip fit. We want the shaft to go in the hole, be able to come back out. We can put these things together. We can take them apart. Okay. But now I want to control the orientation also. So I put another hole, and now this is times what? 2x typical. Right? And so that applies to this dimension. So both holes have the same tolerance and dimensions. What do I also have to do now? If I'm going to make the 2 plates, I'm going to make the 2 shafts. I have to know the distance between them, right? So I have to be able to measure this distance in order to be able to assemble both plates together and put both shafts in. And so let's say this is 5 inches. What does the tolerance on 5 inches have to be?
.1 inches, plus or minus.
All right, so it's 5. So we say it's 5 plus or minus 0.01. So that means that they could be, so 1 plate, because now we got 2 plates, right? That are fitting together. This one could be 5 plus 0.01, and this one could be 5 minus 0.01. So what's that? 4.99, right? So this one's 4.99, this one's 5.01, and the shaft is 1. Can we still assemble them?
No.
We'd have to make the shaft smaller or make the tolerance on location tighter. Is that correct?
Yeah.
We made the shaft smaller. It's who's experienced this when putting together something, especially if you drilled the holes yourself and you're trying to put screws in. So you guys could figure out what the tolerance has to be based on what we know, correct? So what happens when we add a third or a fourth hole?
It gets a lot harder.
It gets harder to understand. Now, one of the things that we can do though is we can, but almost all of you said that you've designed something before, right? You've sketched it. I'm assuming that most of you that have designed and sketched something have also built something based on your design or sketch. Did you go and figure this all out every time? No. Did it always work? Didn't always work either. So if you want it to work, you should figure it out. Now, do you have to? Yeah, you do. If you want it, if you always want it to work, you should figure it out. Based on what we showed here, you can figure it out. Now, let's just think about, let's see, when we come to lab, I've got a good pass around. I pass around in the class, but I'll have you guys, I'll have it out for labs later this week. People, yeah, everybody's coming to lab again this week. So I'll have that so that you can check it out when you come in and out of the lab. I'll show it to you right now. So I've got a piece of stainless steel with a bunch of holes in it. I've got a dowel pin. If I put it in this hole, I can wiggle it around. You guys, maybe you can hear it if I hold it up to the microphone. I put it in that hole, I can wiggle it around. If I put it in this hole, I cannot wiggle it around in the hole. The holes aren't the same size. And what we've got here is we can standardize the type of fit that we're talking about so that we can discuss it. And so these are all slip fits. And if we go to the Machinery's Handbook, oh, look at that, I had a magic link. And the link still works. I made the slide a long time ago. Dimensioning, gauging, that's not the one. So we learn about ANSI drafting practices. Here we go. Allowances for tolerances and fits. Allowances for tolerances and fits. There's a lot of text here. You can read it. There's a definition of a basic size, a tolerance. You might need to know that stuff. Unilateral and bilateral tolerances. Application of tolerances. Let's get to the good stuff. Oh, here's, you can figure out how much pressure it would take to put those two things together if one of them is bigger, if the shaft is bigger than the hole. There's pressure factors for forced fits. How hard do you have to press on it? Let's see what else we got down here. Factors for calculating shrinkage fits. Here's a cool thing. You take the pin and you put it in the freezer, and you take the thing with the hole in it and you put it in the oven, and then you pull them out. You drop the pin in the thing with the hole, and then they all both come to the same temperature. The pin has expanded because it warmed up. The thing that came out of the oven has contracted because it got cooler. And now those things will come apart, but you didn't have to use pressure to put them together. It's kind of cool. They use that with rivets and airplanes a lot. Shrinkage fits, yeah, we can look at these things. But what I want to get to is down here. Here's a, there we go. And so this is a graphical representation of some stuff that's in a table that's also in here. But this is, so the running or sliding fit. So that means we want the shaft to be able to go in there and be able to move around. We can take it back apart again. And so these running or sliding fits, you can qualify them. So so this one is an RC1 and this one is an RC9, just like on the graph. And so in the RC1, we put it in and it doesn't jiggle. And in the RC9, we put it in and it does jiggle. So the partially shaded stuff that on the top there, that means how big is the hole. The blacked in stuff on the bottom, it means how small is the shaft. And so you can see there's a gap between the biggest shaft size and the smallest hole size in that RC9. Well, there's a gap all the way down because these are running and sliding fits. So that gap is the allowance. That's how much is allowed to jiggle in there. And so you can find these numbers out. And then if you go to the tables, so that's a graphical representation that sort of gives you an idea of it. But if you go down to the table and you say the nominal size, so the nominal size of my hole / shaft is between 0.71 and 1.19, then I can know that the hole needs to be 4 bigger, so between 0 and 4 bigger, and the shaft needs to be between minus 0.3 and minus 0.55 smaller to get this type of fit. And these numbers are in thousandths of an inch down here. So what's minus 0.55 thousandths? It's about 5/10 thousandths, right? So you gotta remember that these numbers are in thousandths of an inch when you go through the graph. But now, when you're designing a part for your MQP, you could go to the machinery's handbook and decide how big the hole needs to be for the type of fit that you want it to be. And then if you've got 4 of these, based on what we drew on the board here, you could figure out what does the dimensional tolerance on the location of the hole need to be so that the whole thing fits together. All right, so that's, look it up in the machinery's handbook. Go back to the slides.
Time.
Oh, it's almost perfect because I was thinking I was done. I was just checking the slides to see if I missed anything. Yeah, we already talked about all this stuff: trueness, precision, accuracy. On Thursday, we'll start with this slide. I just want to finish up a little bit on this topic. But
Also, I missed the last thing you said just a few minutes ago. What did you want us to look up in the machinery's manual?
if you are designing something and you want to know what's the correct tolerance on the shaft that I'm designing, or what's the correct tolerance on the hole that I'm designing, you can look that up in the machinery's handbook.
Okay.
And it classifies it. Those are as defined by standards. Yeah, I think that's good. So no lecture tomorrow, but I will be on tomorrow to talk to people that are entirely at home about lab stuff. So I'll be on at 11 o'clock tomorrow to talk to people that are working from home this term. If you're working from home and you can't make it at 11, then we'll figure out another time. I'll talk to you about that. But we'll work out what we're going to do to make up for the fact that you didn't get to go run the machines. All right. So I'll see you guys on Thursday. On Thursday, we'll talk about the football stadium. And then we'll talk about, what are we talking about on Thursday? Oh, functional design. Perfect. That's a great segue into functional design. All right. And if those got questions, I'll stick around for a few minutes.
Are lab times still the same?
Yeah, lab schedule is going to stay the same unless if you have a problem with your lab schedule, then let me know. We can switch it around. But I figure it's simple if everybody just stays at the same time each week.
My inbox got bombarded with a bunch of auto notices, so I ended up missing what you shared on the screen. Where do I go to look up some tolerances?
It's in the machinery's handbook.
Yeah, what chapter I'm in?
Yep.
I should have specified that. What chapter?
Yep. Yeah, I'm getting back to it. So you want to find the section on dimensioning, gauging, and measuring. And then there's a section called allowances for tolerances and fits.
Okay.
And the one we were looking at was down here.
Whole basis?
For whole. Yeah, I think this is where somewhere in this range is where we were. And you can look through the section, but it talks about different types of fits and things like that, for all that. So we'll talk more about this as we do the functional design part on Thursday.
Cool. Thank you.
Professor, what would be the best way to measure at 5 inches on your part, behind the part you drew behind you?
To measure the 5 inches between
Yeah.
the holes?
Yeah.
The best way to do it. It depends on the tolerance.
Okay.
So if it's, and it's true. So one of the things when we, at our company, when we quote parts, we won't tell you how much it's going to cost to make the part until we've figured out how we're going to measure the part. Because sometimes measuring the part is as expensive as making the part. So if your tolerance here was plus or minus 1/4 of an inch, then you'd use a ruler. Just hold up a tape measure and say, yep, I got it. And usually I would measure from this edge to this edge with the tape measure. If it's plus or minus 0.002, I would use a 6-inch caliper to measure again from this corner to this corner or something like that. And then if I was really worried about it, I might measure make sure the holes were actually the right size when I measure it from one side to the other. If your tolerance is plus or minus 5/10,000, then I might add, I mean, you might have a CMM, coordinate measuring machine, but 5/10, you're getting close to the ability of the CMM to measure it. What I might do is I might take a pin that is a RC1 or something, a locational fit, and put the pin in, and then measure with like a micrometer the distance from the outside of each pin to each, and then you have to do some math to figure out what the center line distance is. So it can be, but you shouldn't have 5 inches plus or minus 5/10,000 on anything. If the designer has done that, it's probably a bad design for location on the holes. But when we talk about functional design, we'll talk about a lot of bad designs that I've seen.
All right, thanks.
All right, cool.
Professor, I'm having a hard time finding the CAM 3 assignment. Could
I think I have to click to turn it on.
Oh, okay. I just didn't see it right away. Thank you.
Yeah, I think because they're copied over, but I have to fix the due date. So I'll do that before I log off.
All right, thank you so much. I'll see you Thursday.
Great.
I missed my lab yesterday. I just totally forgot about it.
Is there a way for me to make it up?
So if you're available on Friday from 1 o'clock to 5 o'clock, and then from 6 to 9, there's always PLAs in the lab, and they can help you make that up if that works.
Okay.
Best time to do it.
Yeah, cool. I can do that.
Thank you.
So I need CAM 3. All right. So I just need to fix the date on CAM 3. All right.